Okay, is this working?
Yep.
So, great.
Okay, so let's move on to the next talk. The speaker is Yoshida-san, and he will. Sorry. So he will tell us about decoding monitored quantum circuit and black holes. So please start.
Okay, thank you very much for the introduction. So today I will talk about my recent work on monitored quantum circuits and discuss why it's related to black hole physics. So let me begin with a brief introduction. So let's imagine that we have a product state, like very boring product state, no entanglement at all. Then it is well known that the system will eventually become a highly entangled state after interactions among neighboring qubits. Namely, the state will become a volume law state. And this is essentially the phenomenon we call thermalization. And then, but the question is, what happens if we monitor the system by performing projective measurements during its time evolution? So specifically, we imagine that at each space-time of this discretized quantum circuit, we will perform projective measurement with some finite probability p. P can be anything. And so here is a kind of cartoon I drew. So this one, yes, let me see. Yeah, this cartoon. Right. So then this is a quantum circuit, and the horizontal lines represent like 2 qubit gates, and then these cross marks represent measurements. Now, naively, you might think that the system will remain to obey the area law entanglement because measurement tends to destroy the entanglement and reduce the measured qubit to a product state. And however, quite surprisingly, it has been found that if measurement probability p is small enough, smaller than some finite threshold value, then it turns out the output wave function remains to obey the area, the volume law entanglement. So it's huge entanglement remains. And here, this is like a very typical behavior of the plot of the entanglement entropy. As you increase the subsystem size A, then the system becomes more and more entangled, and it obeys the volume law if the measurement rate is small enough. Okay. Now, previous works have revealed a number of interesting properties about this monitored quantum circuits, mostly based on numerical studies. And there have been only a limited number of analytical studies so far. Now, these findings are quite interesting because it's quite interesting and illuminating because if we remind ourselves that the object we actually encounter in our daily life are actually monitored quantum systems. And, for example, a cup of coffee we drink every day is just after a many-body quantum system, which is continuously monitored by ourselves. So these results are really interesting because it may suggest the possibility that long-range entanglement may play some essential role in physics of monitored quantum systems, such as a cup of coffee, or for us, maybe a black hole. Now, however, there is one important question remaining, which is, if we think that such a long-range entanglement arising in this monitored system is important, then such entanglement must be verifiable. We should be able to see it. This is, of course, because observing the phenomena is a verification of the entanglement. However, up to this point, there is no method to see the entanglement arising in monitored quantum system. And another important question is the underlying mechanism behind the emergence of entanglement. And actually, previous works have said that quantum information scrambling is the key. And I think mostly because people used hard random unitaries to study monitored quantum circuit. But we know that, well, thermalization is growth of the entanglement is thermalization, while growth of the operator is the scrambling, and they are different things. So the connection between scrambling dynamics and entanglement in monitored system is really unclear at this point. And of course, we want to know the relation to black holes.
Sorry,
Now,
Benny, can I ask you a question?
Yes.
So I don't think I understood the motivation a little bit when you brought up the cup of coffee. As you said, a cup of coffee is like a system we monitor a lot, and that one has volume law entanglement or volume law entropy anyway. So isn't it expected that you should get volume law if you don't observe something?
No. This is a closed system. So it's a cup of coffee might be entangled with the rest of the universe. That is known. But we look at the closed system. Still,
I see.
Yeah.
Sorry. Thank you.
Yeah, I should have explained. Yeah. So this phenomenon is quite exotic. Now, so in this work, I want to provide some progress to these problems. So first, I will present a decoding procedure or verification procedure to see the entanglement. But this work is limited to what we call the Clifford circuit. And some of you may have heard of Clifford circuit. It is a subclass of quantum circuit which transform Pauli operator to Pauli operator. And so that's a kind of toy model which is solvable, and then we often use it to deduce like entanglement and scrambling properties of many body systems. And for this system, I can provide a complete decoding algorithm. And in fact, you will see that this decoding procedure clearly reveals why the entanglement growth in monitored system is actually related to quantum information scrambling. And you will actually see that it is really related to out of time ordered correlation functions. And also it is not the unitary circuit which is creating the entanglement, but it's actually the measurement which creates the entanglement. Now, of course, if we learn something new about many body condensed matter system, we want to think about black holes. So here I want to point out that this physics of a monitored quantum circuit can have some analogous situation in the Hayden-Presky recovery problem, or in other words, information recovery from black holes. Okay, so this observation actually suggests that our previous results on Hayden-Presky recovery algorithms and so on can be actually used to verify the entanglement in monitored quantum systems. And this goes beyond Clifford as well. And also it teaches us some interesting lessons about the nature of the black hole interiors. Okay, so that's a kind of a quick summary of my talk. So now let me move on to the actual content. So I will begin with verification of the entanglement. Okay, so let me explain the setup. So given the output wave function of monitored Clifford circuit, you have a wave function. The central question is, of course, we want to understand if a subsystem A is entangled with the rest of the system B. And the main technical result is that this problem of entanglement verification can be mapped to a certain dual classical error correction problem. And this corresponding dual problem is constructed by examining the kind of space-time pattern of out-of-time ordered correlation functions. So let me explain the setup. It may look a bit abstract, but it's pretty simple. So here, instead of starting from a pure state, like a product state, I will instead start from maximally mixed state. Okay. So, or you can actually instead prepare EPR pairs, and by preparing the reference systems, and yeah, so then this will create a maximally mixed state on the system. But still, I'm interested in the entanglement within the system. Now, by using so then we keep measuring the system, and then but by using the Heisenberg picture, we can just simply represent this circuit as a sequential measurement of Pauli operator P1, P2, P tau, and so on. these are in the Heisenberg picture. And so these are time evolved operators. And this pi is just a projection operators. Okay. So it's just my circuit is just repeated application these pi operators up to tau. Tau is the last operator we are applying. So it's pretty simple. Now, here, if you want to study the case with the product state as an initial state, then actually you can just measure all the qubit at the beginning, like every qubit with z basis, and it will reset your initial state to, let's say, all zero state. So this setup can explain everything, like we would be interested. Now, in this talk, I will look at some quantity called about conditional entropy, and it's just some measure of entanglement, and it's defined in this way. So we always write it with A, B with this vertical line. It is SAB minus SB, and well, I didn't know much about this quantity until a year ago, but the key point is that for classical system, this quantity is positive or zero. But for quantum system, this quantity can be negative. And this quantity is lower bounded by minus of the entropy of A, and so on. But the point is that if this is very, very negative, then you see that there is a lot of entanglement between A and B. And in fact, if SAB, this conditional entropy is maximally negative, then you can show that the mutual information is maximally maximum. So it's maximally entangled. So roughly speaking, negativity of conditional entropy means strong entanglement. And that's all we need to know. Now, I would like to turn to the construction of the dual classical error correcting code. And again, this may look a bit complicated, but it's pretty simple. So I want to emphasize that my task is I want to understand the entanglement between A and B, two subsystems in my system without involving the reference. Now, to construct the code, I will study scrambling. Namely, first I look at this subsystem A and then pick some Pauli operator PA. This can be identity X, Y, Z, and so on. But I just pick one of them, arbitrary operator. And then I will study its commutation relations with respect to past operators. So in the past, in this example, I measured P1, P2, P3, P4. So then I can study if my PA operator commute or anti-commute with these past operators. I can construct binary vector. 0 means commutation, 1 means anti-commutation, but it's just a sequence of 0 or 1 binary numbers that I can construct. So I will view this as an encoding that is given a Pauli operator PA. I can encode it into some binary sequence. That is my classical error correcting. So my code word or this sequence is just a record of commutation relations. Now you can already see that this classical error correcting code, in order for this classical error correcting code to be robust against noises, you need scrambling, because without scrambling, these code word will be all like 0, right? But we want to have some non-trivial code word, so yeah, we need scrambling in order to have a robust encoding. So this is the definition of the code I'm considering. It's just a space-time pattern of autox, because yeah, I want to emphasize that commutation relation is just essentially auto. So it's just a space-time pattern of scrambling. Now, the remaining task is to specify the error model, and this part often generates some confusion and misunderstanding. So I want to proceed a bit carefully. So I think when we study error correcting code, we normally consider errors which randomly act on each qubit. But here we are not doing that. Okay. Here we are not considering such random errors. In fact, the form of possible errors that may act in this system is completely determined by the measured Pauli operators. So let's recall that we have measured P1, P2, P3, P4, and so on. This set of operator with this causal ordering actually completely specify the possible form of errors. So let me explain how to do that. It's again, you can actually just look at the commutation relations among these measured Pauli operators. But there is one subtlety. So we always look at the commutations with respect to past operators only. We don't look at the future. So for instance, P1 is the Pauli operator that was measured at the very beginning, So there is no past operators. So we put 0. So it's a trivial thing. But P2 is the operator that was measured for the second time. So I still need to look at the commutation with P1. So there is one past operator. Okay. And I just keep doing that. And then for P tau, the final operator I measured, everything is in the past. So I need to look at the commutations for everything. But the point is that by doing this, I can construct the error vectors. And these binary vectors are actually the possible form of errors. So this error vectors looks like a kind of together lower triangular matrix. And then by looking at each vectors and its linear combination of these vectors, you can form a space, a group of possible error vectors. So I'm just assuming that these vectors may possibly act as an error to my code word. So that is the error model. So here's the summary of my classical error correction problem. So first, I had the Pauli operator PA. It's on subsystem A. Now I will encode it into binary vector by looking at out of time ordered correlators. So this is auto. And then this auto will be acted by error vectors. And then these error vectors come from one of the error vectors contained in this error vector set. And then the question is, given the outcome of this thing, can we still reliably recover the Pauli operator PA or no? That is the problem I am interested in. And I'm claiming that this problem is dual to this entanglement problem. Now, I think it's useful to look at some cartoon figure. So I have two Pauli operators, PA and PA prime. And then these code words, initially, maybe they are different. Okay. So if there is no error, I can distinguish them. But there is an error vector acted, so E and the E prime. So these two vectors may get moved to other points. As long as these, so you can draw a sphere of possible vectors. And then as long as they do not overlap with each other, I can reliably reconstruct if it was PA or PA prime. So this is like the error correcting criteria. All right, so that is the idea. Now, let me mention one of my result. So when this dual, so roughly speaking, it says the following. If the dual code, this classical error correcting code, can tolerate errors, then A and B are strongly entangled. Namely, this can be turned into a formula, which is pretty precise. That is a conditional entropy, SAB, is always given by minus A. It's the volume of A, so number of qubits in A, plus log 2 NIA, where NIA is just a number of Pauli operators, which become indistinguishable from identity operator, right? So that is like, because of the error, your Pauli operator PA, you don't know if it was Pauli operator PA or identity operator. You count such Pauli operators and that's the number of NIA. So very roughly speaking, NIA is like number of lost info. Yeah. And then, so that is the formula. So I can emphasize that if this code can tolerate all the errors, then NIA is equals to 1 because identity operator itself should be counted. So it's 1, which means that log2 of 1 is 0. So this conditional entropy becomes maximally negative, which means that A and B would be maximally entangled. But the point is that this formula holds for any situations. Now, I guess it's too technical, so let us look at one example. This is the example I think everyone knows already, but let's look at it. Just 2 qubit, so A and B, 2 qubit. And then we are going to measure this 2 qubit with these two operators, ZZ and XX. Then what happens? Now, my recipe says that I should pick first the Pauli operator on A, identity X, Y, Z, and so on, then study the commutations. So identity operator commute with all the operators, so 0, 0. But X, A operator anti-commute with P1, because it has Z, but commute with P2, so 1, 0. Then Y operator, 1, 1, Z operator, 0, 1, and so on. Then now you see that my Pauli operators I, X, Y, Z are mapped to a unique code word 00, 10, 11, 01, and so on. So there is no loss of information in the encode. Now in this program, actually error vector is trivial because P1 and P2 commute with each other. So this error vector I discussed, it's actually, you don't need to consider in this situation. So there's no error. So encoding is unique, so there's no information loss. So this means that the system should be maximally entangled. And this is indeed the case because P1 and P2 are basically Bell basis operators. So the outcome you get is one of the Bell state. So for example, if P1 is +1, P2 is +1, then you will get this EPR pair 0, 0, +1, 1. This is how it works. Okay, so I have shown that the entanglement in monitored quantum circuit sort of emerges from the recoverability of the dual code, and this code was constructed by looking at scrambling. Now, next task is to actually see the entanglement and check if they are actually entangled. Now, the easiest way to verify the entanglement is, of course, distill EPR pairs. And so I want to discuss how to distill EPR pairs. And so in order to distill EPR pairs between A and B, we can just simply perform the same measurement, but in the reverse order. So actually, I wrote down the protocol in this diagrammatic form, and then this pi is just it's just a concise notation of all the measurement. Sorry, all the measurement. Yeah, from 1 to tau. And then here I do the reverse. That is, yeah, I think this is much better. So I first measure P1, P2, and so on, then P tau. And then in the reverse measurement, I do P tau minus 1, and so on, P2, P1, and so on. Okay, so I do the reverse. So that is the protocol. It's pretty simple. And then now let me denote the measurement outcomes like M1, M2 is the first round measurement, and the second round measurement with bar, M1 bar, M2 bar, and so on. Okay. Now, given these two rounds of measurement, M and M bar, which are vectors, you can construct a sum vector that is, you just add up two of them. The point of computing the sum is that if sum is 0, then you know that M and M bar, the measurement were the same. Now, one thing you might immediately notice is that with two measurement outcomes, M and M bar are identical to each other, then it turns out that the EPR pairs are already distilled on this A and A bar. And this is essentially same as the Hayden-Prestio recovery algorithm from myself and Steph. So in this case, it's distillation is already done. So it's pretty simple. But what about the case with, sorry, it's not equal. Yeah, M is not equals to M bar. And then in that case, we need to apply some feedback operation. Okay. So this feedback operation acts on one of the qubit. So the question is how to find such a feedback operation. And then here we need to use this error correction property. That is, this S vector, which was a summation of the first round and the second round measurement. I view it as an outcome of my classical error correction problem. That is, I encoded Pauli into some code word and some error occurred and I got this S vector. That's how I view S vector. Then in this interpretation, I should be able to recover the original Pauli operator PA by decoding these sum vectors. It turns out this PA you find from this S is the correct Pauli operator you need to apply in order to do the distillation. So this is a feedback operator. If you do that, it turns out that you can distill EPR pair on A and A bar. So roughly speaking, decoding of this dual classical error correcting problem is actually a distillation protocol of the entanglement for the monitored quantum circuit. So finally, I want to just briefly mention that this distillation algorithm has several other applications. Yeah, this may be more of interest for condensed matter theorists, but let me just briefly mention that. So for instance, this method can be used to detect the so-called dynamical purification transition. That is, we entangle the system with the reference system, but instead we just prepare only one qubit of the reference system and entangle it. And then we run the monitored quantum circuit. And then the speculation is that if the system is in the volume law phase, this entanglement between the system and reference would be very protected. So it stays there. But in the area law phase, that entanglement may get easily destroyed. So by studying the mutual information between the system and the reference, maybe we can detect the volume law versus area law transitions. So this is the beautiful idea by Glantz and Hughes. But the point is that for this one, they didn't tell us how to do this decoding problem to see the mutual information or entanglement between two systems. But our algorithm can be used to attack this situation. And another important application is, of course, related to the idea of viewing this monitored quantum circuit as a quantum error correcting code. After all, by adding reference system, we can always view it as an encoding of the information from reference to the system. Now, again, in this volume law phase, we expect that the entanglement will be protected from local projective measurement. So in this viewpoint, a monitored quantum circuit can be viewed as a dynamically created quantum error correcting code. So the definition of code keeps changing, construction of the code keeps changing in time. But at any moment of the time, if you are in the volume law phase, you are creating a very good quantum error correcting code. It's a dynamically generated. And then again, by using our technique, actually you can distill the choice state of the corresponding stabilizer code very easily. So yeah, it has some nice applications, and these can be potentially used in actual laboratory experiment if you want to try this idea. Okay, so that's roughly the end of my first part of the talk. So I argue that this entanglement in monitored circuit indeed emerged from scrambling. And here it's very important that you perform measurement, right? Because my starting point was that maximally mixed state, and even if you apply any unitary or maximally mixed state, you don't create any entanglement. So you really need to measure the system, purify a little bit, and then you create entanglement. So here it's really the measurement is the key. And without the measurement, this type of entanglement will not be created. And I also claim that the decoding of this dual space-time pattern of OTOC gives the distillation algorithm. At this moment, I do not know how to go beyond Clifford circuit, but I'm hoping that algorithm I had with Alexei, like this global search type algorithm can be actually used maybe to attack beyond preferred cases. But for that, I do not know at this moment.
Can I
Okay.
ask an elementary question about
Yes.
you? So if we do so this measurement, then that reduces entanglement. But you are saying maximal entanglement is between A and A bar.
Yes, yes, yes.
So because A and B are decoupled, so A and A bar gets maximally entangled?
Yeah,
maybe
so
I'm missing something.
initially, A and B are in a maximally mixed state,
Yes,
so
yes.
A and B are not entangled. But when we start making a measurement, and then if the system time evolves, scrambling with scrambling dynamics, then that measurement can be act as a sort of the seed, and then that can create an entanglement between A and B. So for that reason, in order for monitored system to have an entanglement, measurement is really necessary. And then I will actually, in the few slides, actually, I will claim that actually this entanglement between A and B is actually independent of the existence of R, in a sense that what kind of initial state you put on R, or you start from a product state, the way A and B are entangled is pretty much independent of the, so it's like a state independent entanglement that you see on A and B, and then that is because of the measurement you perform on the system.
So sorry, I missed that. But so what's the reason A and B get entangled? Because we do some measurement and that cut out entanglement.
Yes, yes, it cut out the entanglement, and then it's so that qubit may become 0 or something, for instance. But then in the next step, the scrambling dynamics kicks in, and then generate a little bit of entanglement. Then we perform measurement, but some of the entanglement is still protected and it keeps growing and growing. So yeah, that's how it works.
So your pi is only projection, is that true? Or pi
it's only
also scrambling?
Pi is a mixture of measurement and the time evolution measurement.
I see. Sorry, I missed that actually. I see. Then
yes.
Also, what's so you relate this measurement of evolution to quantum error collecting,
Right.
So this error is related to what kind of dynamics in original system?
Error is related in a sense that so after this system reaches to an equilibrium, it obeys the volume law, and then it has a volume law entanglement between A and B, but it also retains some entanglement between the environment and the system, and then that entanglement is protected. And then even if we perform local measurement, that entanglement is very hard to kill, and it actually takes exponentially long time too.
And that corresponds to error of this collection. Thank you very much.
Okay, so
question too. Can I ask you a question?
Yeah,
I'm
please.
a bit confused about the setup. So here, you apply the random unitary in the pi.
It's not necessary. It's completely generic in a sense that, so this is the initial setup I discussed. So then P1, P2, and P tau are operators you measured. So I'm writing it in a Heisenberg picture. So I'm hiding all the unitary part of the dynamics. And then those P1, P2, P3, and so on are just measured Pauli operators. Now, what I claimed up to this point is completely general. P1, P2, and so on can be arbitrary Pauli operators. It could be one body operator, three body operator, 100 value body operator, it doesn't matter. But most of the situations in the previous literatures, people study the case where this circuit with 2-qubit Haar random unitaries or how random, well, random Clifford unitaries, and yeah, people study
So
these
that
cases.
why does detailed information of time evolution is not necessary?
Oh, it is necessary. I'm just writing it as like so this is, let's say, P1, P2, and so on. I can always evolve it back to t equals 0, right? I mean, then write it as a Heisenberg picture. So it's like a P1 is like P1 T1. So yeah.
Oh, I see.
Then P2 T1 T2. Yeah. So yeah, it's like yeah. But
And-
so yeah.
Yeah, and for your distillation protocol, do you need to prepare many copies of the state, or just a single copy is sufficient?
Yeah, I think single copy is sufficient. Yes, it's everything is single shot, and I can distill the
But why is it that possible? Because if you just only have a single copy, then I thought the distillation is kind of probabilistic. And
yeah. Usually it's probabilistic, and then that is the where did it go? Yes, so I do the measurement, and then if I get the favorable measurement result, then that happens with small probability. Then I don't need to do anything on the EPR pair is already distilled. But if I don't get the favorable result, then I need to apply some feedback. Then with this feedback, I can always create EPR pairs. So yeah, this distillation protocol works perfectly with single shot.
so the case you need a feedback, you can only distill with some probability.
No. I mean, I can find the correct feedback operator. Right. So if A and suppose that if A and B are maximally entangled with each other, in that situation, this algorithm gives you EPR pair always 100%.
Okay, I will ask you later. Thank you.
It's a deterministic algorithm. All right, so that's the situation. Okay, so let me move on and then talk about entanglement and the quantum error correction related properties. So I will begin by discussing a certain interesting entanglement property from the perspective of state dependence. So far, I have prepared a maximally mixed state as an initial state and studied the entanglement property on a very generic ground. But here, instead, I will consider the case with product states as initial state. So instead, I will prepare like O0 state and so on. Then what happens? Now, the question is, naively, you might think that the entanglement between A and B, the way they are entangled, will depend on the choice of the initial states. That's probably how you would think. Namely, like if you switch to other product state, 000 or 0110 or something, then you might think that the A and B entanglement, the way they are entangled may change. But it turns out that this entanglement arising in monitored circuit is largely independent of the initial state, especially if they are already in a volume law phase. Namely, my claim is that in the volume law phase, A and B entanglement is independent of the initial state when A is smaller than the certain length scale, which is essentially the code distance of the dynamically generated quantum error correcting code. Now, the argument is quite simple. It's actually from the definition of the code distance. But here is again monitored quantum circuit with reference state. So initially it's entangled with the reference. But the point is that if A is smaller than this secret length scale, D code, it turns out that the mutual information between A and the reference should be equals to 0. That's actually the definition of code distance. Okay, so that means that any action you do on R, the reference cannot affect the AB entanglement. So that is what we call decoupling of A and R. Then if this is a case, then you can just project this reference into O0 state. Then you will get the situation with the product state as an initial state. But the point is that since R cannot influence anything about the AB entanglement, so the way A and B are entangled remains the same, even if you project the difference into a product state. By saying like the entangled in the same way, I mean that the same distillation protocol can be used and you can always see the EPR pair. So it's really they are entangled in the identical manner. So this means that actually the quantum error correction property of the monitored circuit implies that the entanglement arising in the system is mostly state independent. It doesn't care if it's entangled with the reference or it's coming from certain initial state or so. So in the language of the black hole, of course, this says that one-sided pure state young black hole or old black hole, it doesn't matter how A and B are entangled with each other if we are monitoring the black hole. But before going to black hole, I think we should still discuss a bit about this condensed matter problem. So so the point is that I argue that there is a cold distance scale. Below that, everything is state independent. Okay, but this distance scale is actually quite large, and it is known that in 1D random circuit situation, this decode scales like n to the 1/3, and this 1/3 has some analytical origin, but apparently it has some analytical origin. But the point is that it's not thermodynamic quantity, but it's not a constant. It's pretty big quantity. And for zero-dimensional system like O2 coupled system, so a Brownian type circuit with measurement, it turns out that this cold distance scale is actually order of n. It's not like order n. So it's pretty big. And the point is that, so this means like for most of the length scale we would be interested in, yes, the entanglement within the system is actually state independent. And only at the scale which is very, very big and complicated length scale, this entanglement becomes state dependent. Now, I have argued that this entanglement does not depend on the choice of the initial state, but it turns out that it does not depend much on the measurement outcomes in the far past as well. The reason is very simple. Suppose that this is the circuit running for quite a long time. Okay, this is time. Then here's this red region is a recent measurement, and then the past is like other measurement that happened in a long time ago. But the point is that I can view this part, like past measurement, as a part of the initial state definition. Then in this interpretation, you see that whatever happening in the far past, it just doesn't influence the entanglement between A and B. So the entanglement between A and B are really like generated fresh from the recent measurement. And then there is a decoupling from the past. And of course, this situation changes suddenly if you increase the region A to a bigger region. Okay. Then if A becomes bigger than the cold distance, then suddenly this A-B entanglement starts to depend on the past measurement outcomes. Now here is kind of a cartoon picture again. This is a plot of entanglement entropy, schematic plot of entanglement entropy for subsystem A. Then the point is that even if it is initially a product state or maximally mixed state, if you plot SA, you always see a volume law scaling. But at the cold distance scale, there is a very important change in the nature of the entanglement that you won't see, you cannot see just by plotting SA. That is, up to this decode, your entanglement is state independent. but beyond that scale, your entanglement becomes state dependent. And it's, I think, interesting to point out that this state-independent entanglement is relatively easy to decode, but state-dependent one is difficult to decode because it depends on all the histories exponentially long time ago. So it seems that there is an interesting sudden phase transition on the complexity of decoding, which may have some interesting holographic implication. I don't know. Okay, so here's a brief summary of what I just said. So entanglement below the code distance scale is state independent and history independent and possibly easy to verify, but above the code distance scale, it becomes state dependent, history dependent, and difficult to verify. Now, my speculation is that if entanglement in monitored systems, like a cup of coffee or black holes, if such an entanglement plays some essential role, then that entanglement should be state independent because it should be easy to verify and it shouldn't be affected by whatever happening in the rest of the world. But that is just a speculation. Okay. Okay, finally, let me quickly discuss the relation to the black hole physics. So our favorite Hayden-Preskill problem and black hole interior. Let me briefly recap what was the Hayden-Preskill recovery problem. You prepare an old black hole. So black hole is maximally entangled with early radiation. And for such an old black hole, we throw a diary, and then we try to recover this content of the secret quantum diary by collecting the late Hawking radiation. Now, but in this setup of the monitored quantum systems, we want to think that we are not just collecting the Hawking radiation, but we are actually measuring the late Hawking radiation projected in Z basis or whatever. Okay. Then what happens? Then I can write down this as a quantum circuit, which is something easier for me to understand. So let me do that. So here, this A is a diary, right? So you prepare EPR pair with reference and then send one of them into the black hole. B is a black hole, which is maximally entangled with early radiation. Then along the way, we perform measurement. And then these are viewed as like late Hawking radiations you measure, for instance. Then recoverability in the Hayden-Preskill is just the entanglement between A prime and B bar. So B bar and A prime. Okay. If they are entangled with each other, then your diary, our Alice's secret diary, can be actually found somewhere on the early radiation. Okay. Now, why is this related to monitored circuit? It's just because you again just rotate the whole diagram, then it's identical, really. So you just do the same process in the reverse chronological order, and then Hayden-Preskill problem can be viewed as a monitored circuit. That is, in the monitored circuit, I asked if A and B are entangled with each other, which is exactly the same problem as A prime and B bar are entangled with each other. Okay. So the fact that in the monitored quantum circuit, you can retain a lot of entanglement up to the code distance actually suggests that the Alice's diary is also safe and you can find it in the early radiation. Now, the bonus of this observation is that you can do decoding of the Clifford black hole. So for this, unfortunately, it works only for Clifford. And I know that black hole is not a Clifford circuit, but still, it may tell us something. So you just do the same thing, and it's our old Hayden-Preskill recovery algorithm. But you do the measurement here and here on two sides, and you compare the result and send the feedback, and you can recover the diary. Okay, so that's one connection to black hole physics. Another connection to the black hole physics is an interior problem. So in this case, again, we can view a black hole or the black hole. And then, but in this case, we are really like monitoring the black hole. Maybe we are taking a picture of the black hole or something. And then there's a late Hawking radiation A, and I'm interested in its partner mode. I want to write down its partner mode in the language of the outside quantum mechanics while I'm taking a picture of a black hole. Okay. Then this is a circuit. Then I'm asking if A is entangled with B, and if it's entangled, which degree of freedom in B is entangled with A. But you can actually see that this is indeed the interior reconstruction problem, because I'm defining the interior Hawking partner mode as an entangled partner of A. So yeah, if you find the EPR pair partner on B, then that is your Hawking interior mode. So all the decoding algorithm I mentioned and so on can be used to reconstruct the black hole, the Hawking partner, and so on. Now, I want to emphasize that this AB entanglement you see here, of course, it can be found on B, but it can be found on B means that it can be found inside the black hole without ever involving the RE radiation. Okay, so this means that you can again collapse or completely remove RE radiation and then bring it to a pure state. This means that the expression of the interior partner mode you get in this situation under the continuous monitoring, it's actually completely state independent below the cold distance scale. That is, either it's a young black hole or old black hole, it's state independent, so we are free from any typicality paradox if the system is continuously monitored. Okay, so that's all I wanted to say. So the summary is that well, entanglement in monitored systems comes from scrambling, and that was, I think, not known. And also entanglement verification can be viewed as a decoding of the dual code. Unfortunately, this dual code description works only for Clifford circuit. To go beyond, maybe we need to go to quantum dual code or whatever, I don't know. And so I also discussed that there is an interesting transition between state independence and state dependence on the entanglement. And so I think this is something interesting to look at from the perspective of black holes. Maybe you can think about continuously monitor the SYK models and so on. It might be interesting things to study. Okay, well, thank you very much. That's it.
Thank you. Any question or comment?
Can you generalize this projective measurement, weak measurement?
Weak measurement. Let's see. So in a generic setup of this monitored quantum circuit, physics of monitored quantum circuit, yes, and people have generalized it into weak measurement in some form. For instance, this is qubit, but you go to QD, let's say multiple state spins, and then instead of collapsing it into a pure state, you can collapse into some subspace. That can be done. Also, there is a more like a continuous version of this monitored circuit where people study what people call Brownian circuit. That is like you apply random 2 qubit Pauli unitary rotations continuously, and then we see it, how it evolves, and then you add just a bit of a projection in that formalism, and then this setup is actually analytically solvable, and it was solved, and it has some nice coding properties. I think it was done by a student of Brian Swingle, I think, for that one.
Well, do you expect the time that the state independence becomes shorter? In the case of weak measurement?
Let's say that's a good question. So if we perform, yeah. So let me see. It's tricky. So yeah. So let me think. So so if I make lots of measurement, then so measurement rate, right, is low versus high, and then if measurement rate is low, then we retain lots of entanglement, but the code distance, I believe it becomes low and high, and then that's because if measurement rate is high, then you are sort of like training the circuit, and with lots of noises, and then the remaining thing is really protected. That's because it's there. Now the time scale to reach the equilibrium, I do not know. I do not know the time scale to reach the equilibrium. But what I actually recently found is that for this monitored quantum circuit systems, we actually studied like a growth of the stabilizer size under this measurement circuit, and it's actually superluminal in a sense that it goes like t to the 3 over 2. So there is a faster than speed of light growth of the stabilizer size. But this is perfectly fine. It doesn't violate causality because we are doing the measurement, and in order to know the stabilizer, you need to know the measurement outcome, which can travel only at the speed of light. But there is something faster than speed of light in this physics. I don't know if this, so there are important time scales, 2 time scales. I believe that there is L is the linear length of the system versus L to the 2 over 3. So there is 2, and I believe L to the 2 over 3 is the length time scale to reach the code equilibrium. Yeah, I think.
Okay, thank you.
Sorry, I just had a quick clarification question, Benny. In the Hayden-Preskel thing, it sounded like you're doing something different. I thought that usually there you wait until all the early radiation comes out, you throw in a diary, and then you have to wait a little bit just for a few bits to come out. But you were talking about
yeah. So it's like it's more like you don't really wait. You start collecting the Hawking radiation and keep measuring. But the point is that this setup is quite general, so you can wait for a little bit of scrambling time, and then you start collecting the qubits, and then yeah. I think like the most important thing is like problem structure is the same, and yeah.
But you do have, sorry, just to make sure, you do have to wait a little bit after you throw in the diary before it's encoded, right?
Yes, in order to do the successful recovery. And then if I don't wait, then I can't reconstruct it. And then also there is a possibility of actually like I'm destroying the diary by measurement. If diary hasn't scrambled yet, so there is such a risk. But all I'm saying is like, yeah, so this is related, and yeah. So I think let me put it this way, like Hayden-Preskel program, previously you catch Hawking radiations, and then these Hawking radiations are qubits, and all the operators supported on these qubits are commuting. But in the monitored situations, these qubits in different times, they could be anti-commuting, not commuting with each other. So then this monitored circuit formulation can allow us to attack such situations.
I see. All right, thank you.
Any other questions or comments?
I saw something in the chat.
Yeah, Azuma-san, do you have a question?
I have a question. Actually, then in the original Hayden-Preskel protocol, we need to know what kind of unitary is performed by black hole, right? To decode.
Yes, that's always the case. Yes,
yeah,
we need to know.
In your case, what kind of information is needed to decode?
I need to know the black hole or the dynamics And also I need to know the measurement outcome.
Okay. We need to
So-
wait until that the outcome is come out in some
Yes,
sense.
so I need to make a measurement. I need to keep recording the measurement because yes, so I make a measurement. Was it +1, -1? That information should be kept. And, otherwise, it's like a measure and forget channel, and it destroys the information.
Yeah, your coding is like based on the we want to but by performing the projection measurement, we can initialize some step, right? That's my your code is based on cutting the entanglement between A and R in some sense, AB versus R, right?
Yes, so in that case, you are right. So A was initially entangled with B, but by making measurement, that entanglement is shifted into B bar.
Okay, thank you very much. Yeah.
Can I ask a question? So in your final model about the recovery of black hole interior, do you have any suggestion to maybe gravitational interpretation, like so how to get inside like island or some other type or some entanglement wedge?
Yes, right. So the short answer is I do not know, but I think like making a measurement, introducing some debrain and so on, that might be an interesting way to approach and then try to understand the back reaction. But I do not know. I think that making a measurement pushes the boundary a bit inward and so on. That might be possible interpretations, but at this moment I do not know.
Also, so your result depend on how this measurement distributed spatially.
It depends, and then if we do a bad distributions, then yes.
So you assume some more kind of homogeneous or quite random distribution, or
quite random distributions, and it's important that the information about A, in this case it's late radiation, Hawking outgoing mode. If I do a bad measurement in the past, then it actually sort of destroys the entanglement. So I need some sort of entanglement and scramble. But this is usually the case. So I mean, even for a short period of time, it scrambles pretty quickly. So it should be fine. But the size of the operator grows very quickly and exponentially from the beginning. So I believe it's not a big problem.
I see. Thank you very much.
Any other questions or comments? All right. If not, let's thank the Yoshida-san again.
Thank you very much.
Thanks for the great talk. Okay, so this is the end of the evening session. And okay, so I put the link to the spatial chat again. So if you want to further discuss, let's move to the spatial chat room. And all right, thanks for the participating. And okay, so let's close this evening session. Yeah, thank you so much.
Thank you very much. Okay, so I will close this Zoom pretty soon for recording.